Let's discuss the Gaussian distribution. There is a good chance that you are familiar with the Gaussian distribution in some context. It's more commonly referred to as the normal distribution or the bell curve. Both terms have roots dating back to the 1800s. The term bell curve was brought to prominence in the mid-1990s with the publication of the book The Bell Curve: Intelligence and Class Structure in American Life, a book you may or may not remember. It was a best-selling but somewhat controversial book. The term Gaussian actually refers to Carl Friedrich Gauss, a prominent German mathematician and scientist who derived the distribution in 1809 to describe the error curves for planetary orbits. Let's return again to a slide from the introductory module about the process of data analysis to provide some context for our discussion. We have a hypothesis. We identify a population of interest in which we conduct a design study. We collect a random sample of data from this population and calculate descriptive statistics. Next, we are ready to make population inferences. The process of making inferences generally involves the calculation of p-values and confidence intervals, which in turn generally involves making some assumptions about the behavior or distribution of the population values we are trying to estimate and make inferences about. These assumptions are formalized mathematically and make possible the calculations that generate p-values and confidence intervals for the population parameters of interest. Let's say we have a population of interest, and let's say our interest lies in a continuous measure in that population, say weight in kilograms or systolic blood pressure. A common assumption is that the distribution of these values in the population follows a Gaussian or normal distribution. The normal curve provides a description of the weight or systolic blood pressure distribution in the population from which we draw our random sample. The Gaussian distribution is special for a number of reasons. This distribution is naturally formed when multiple sources of variability act independently and additively. This is actually the motivation for and message in the title of the Bell Curve book, that IQ scores are normally distributed because a person's intelligence is the sum of many small random variations in genetic and environmental factors. Because scatter or error is often the result of many independent causes, assuming that the distribution will follow a Gaussian distribution is often a reasonable assumption to make for a variety of variables. The reasonableness of a Gaussian assumption is fortunate because the distribution is well behaved mathematically. If one can assume a Gaussian distribution, statistical calculations can be greatly simplified. As will be discussed later in this module, the Gaussian distribution plays a central role in statistics because of an important mathematical theorem. Before moving on to discussing some important properties of the Gaussian distribution, let's distinguish between population and sample. In Module 3, we discussed the use of graphical descriptive summaries for summarizing key information about a sample of data. The histogram shown here is generated from a simulated random sample of 100 observations sampled from a normal distribution, done using StatCrunch, and quite obviously has a Gaussian shape. The point I want to make is that the Gaussian assumption we make is an assumption about the population distribution, not the sample. The shape and properties of the sample distribution are inherited from the shape and properties of the population distribution. Here are some points to remember. The Gaussian population distribution shown here is an idealized distribution. In reality, the population distribution for a given variable may be only approximately Gaussian. Graphical plots of sampled data, like histograms, are often used to assess the appropriateness of a Gaussian population assumption. Because of sampling variability, we would only expect a sample histogram to be approximately Gaussian in shape, even if the population distribution is a perfect Gaussian distribution. This can make empirical assessments of population distribution assumptions based on sample data challenging unless the sample size is very large. Let's discuss some Gaussian distribution properties relevant to the course material. The horizontal axis shows the values that can be observed, and the vertical axis quantifies their relative frequency. The mean is the center of the Gaussian distribution. The relative frequency is highest near the mean, indicating that most of the values fall close to the mean. As values move away from the mean, their relative frequency drops, giving the characteristic bell shape. The standard deviation, or SD, is a measure of the spread of the values around the mean. Also note that the Gaussian distribution is symmetric. From previous material we have covered, this implies that the mean and median are identical. A very nice property of this distribution is that it is completely described by the population mean, designated with the Greek letter mu, and the population standard deviation, designated with the Greek letter sigma. As long as you know these two values, you can completely specify the population distribution. We can label the x-axis of the Gaussian distribution in terms of where the mean is located and how many standard deviations away from the mean values are located. The area under the entire curve shown here represents all of the values in the population. We can make some useful general statements about the distribution of values for a Gaussian distribution. About 2/3 or 68% of the values in a Gaussian distribution are within one standard deviation of the mean. About 95% of the values in a Gaussian distribution are within two standard deviations of the mean. Technically, the exact number of standard deviations for 95% of the values is 1.96. I mention it now because the 1.96 represents a special value that we will encounter again in a later module. About 99% of the values in a Gaussian distribution are within three standard deviations of the mean. So how do we use this information in practice? Let's assume we have measured systolic blood pressure on a sample of patients and calculated the sample mean and sample standard deviation to be 135 and 15 respectively. If we assume the distribution of blood pressures is approximately normal, we can infer that approximately 95% of the values lie between 105, which is two standard deviations or 30 points below the mean value of 135, and 165, which is two standard deviations or 30 points above the mean value of 135. I want to also mention a special Gaussian distribution called the standard normal distribution. This is a Gaussian distribution with a mean of 0 and a standard deviation of 1. All Gaussian distributions can be converted to a standard normal distribution by subtracting the mean from each value in the population and dividing this difference by the standard deviation. We call the resulting value a z-score, which represents the number of standard deviations away from the mean. We can relabel the x-axis using these z-scores. A z-score of 0 indicates the mean value, while a z-score of +2 indicates a value 2 standard deviations above the mean. The standard normal distribution and z-scores have a number of convenient uses. For example, they facilitate comparison of values from different normal distributions. A prime example of this is the use of z-scores in CDC clinical growth charts for selected body measurements in U.S. children. Summarizing, let's say we have sample data, maybe blood lab results or survey results. We calculate sample statistics for our data and then use those statistics to make inferences about the population of interest from which we have drawn our sample. If we can reasonably assume that the distribution of values in the population has a Gaussian distribution, we can take advantage of the properties of this distribution in making inferences about the population under study. In the next section of this module, we will discuss a mathematical theorem that greatly elevates the status and extends the application of the Gaussian distribution in inferential statistics. This concludes our introduction to the Gaussian distribution.